We're glad to have David Montgomery here. He's a professor in the state of Washington, University of Washington at Seattle. He wrote a book. First I heard of him was a book called Dirt, which was about the decline of civilizations around the world because of soil erosion. And then, so that was a very, I guess, as soil conservationists, we'd say that was a very negative book. Well, then he came up with the idea of, let's see what we can do. There must be somebody who's doing something right in terms of regenerating our soils. So after interviewing many successful farmers and others across the country, he wrote a book called Growing a Revolution. And this is on bringing our soil back to life. Among the people that he interviewed and spent time with is David Brandt. And David is here. In fact, he just finished speaking in the chapel and will be on the program later with David Montgomery. But other Farmer Dwayne Beck, who we've had speak here, Gabe Brown, who has spoken in Ohio, Guy Swanson, sitting right here with Exactrix. Many of these successful individuals are included in this book, and David's done a great job of what I would call storytelling. It's a very interesting read as well as being a very informative book. And he will be signing this book and two others that he brought a few with him also at the foot of the stairs. You'll see the book set up on a table down there. Well, let's go ahead and get started. His presentation to this session this morning, I think I titled this From Dirt to Regenerating Our Soils. Let's welcome from the University of Washington, David Montgomery.
All right. Thank you, Randall. Let me get this. Let me wake my computer up, see if it actually, there we go. That should work.
Perfect.
All right, we're good to go. Well, the first thing I should advertise is that if it sounds like I'm talking as somebody who thinks it's about 6 in the morning, my time it is. And so I very much appreciate the invitation to come and talk to this conference. I'm a bit of an unusual selection, I think, for a keynote speaker because I'm a geologist. I'm trained to think about very long periods of time. And when I was in college, my professors taught me to ignore the soil because that was the stuff that covered up the good stuff, the rocks that were underneath. And it's taken me a while to come around to thinking that I kind of missed something in my undergraduate education, and that soil is actually one of the most important and undervalued and underrecognized resources that humanity has. For this audience, that's probably kind of a no-brainer. But what I want to do is tell you in this talk today a bit of the story of my intellectual journey, going from geologist, which I still am. I teach geomorphology, which is landscape evolution, how topography forms, sort of the here and now of geology, and the part of geology that actually the soil really matters to. Because the first question you want to know as a geomorphologist is the landscape covered with soil or not? Is it bare rock, or does it have a soil cover on it? And these 3 books, I would not have 10 years ago when I wrote that first one, Dirt, ever imagined that I would have written 2 more books about soil and find myself now talking about a trilogy of books. But in terms of the executive summary overview of it, that first book over there on the left, Dirt, that was a book that was backward looking. It's the kind of book you might expect a geologist to write. It was about the way that societies have treated their land, how they treated their soil, and how soil then was not, their soil was not able to support the civilizations over the long run. That middle book, The Hidden Half of Nature, that I wrote with my wife, Anne Baclay, arose from our recognition about the importance of microbial life in setting soil fertility. It was the part of soil science that I really didn't get when I was in graduate school and took soil science classes. And the third book over there, Growing a Revolution, sort of brings it all home in a way that is a little more optimistic than that first book that was backward looking at the destruction of soil. So forgive me if the first part of this talk is a little depressing. It focuses on that first book. By the time we get to the end, I hope you'll be as inspired as I am at the way that I think that we can turn around the problem of soil degradation on a global scale. So What's the sort of scope of the problem of soil degradation? This is the UN's map of global soil degradation from a few years back. It's created with a very broad brush, and there's reasons to question some of the methodologies that underpin it, but it actually provides a fairly good global overview of why a geologist like myself would look at the problem of soil degradation as an international, truly a global problem. All those the red zones on the map and the yellow zones are areas where agricultural soils have been degraded to some extent. But as I said, it's a painting with a very broad brush. You can go to any one of these red zones around the world on that map and find farms that have actually been improving their soil over the last few decades and completely reversing the pattern that you would take away from just a quick glance at this global map. That's where I want to end up. Then those two things, the pattern you see at a global scale on this UN map and the exceptions to it that are within all those red zones are really the story behind the story I'm going to be telling you today. But if you look at sort of what are the numbers, what are the extent, what's the magnitude of soil degradation as a global problem? Some years ago, David Pimentel at Cornell and his colleagues put out a paper that argued that by the end of the 20th century, so by the end of the period between the Second World War and 2000, or 95 when they actually wrote the paper, soil loss and soil degradation had resulted in some 430 million hectares of land on a global scale being taken out of agricultural production. That's an area about the size of China and India combined. And if you look at the estimates for what the global average since the dawn of agriculture, of land that's been degraded to the extent that it's no longer in agricultural production, you come up with roughly similar numbers, roughly a third of our cropland globally. That's an awful lot of land. If you think about the problem of feeding the world by the year 2100 or 2050 or whatever benchmark you want to assess down the road, it would really be useful to have more the full complement of the world's agricultural land at its native fertility. And this is a problem with the most recent estimate that I've seen referred to in an international report was from 2015, a few years more recent than that 95 study, that argued that we're losing at a global scale some 0.3% of our agricultural production capacity each and every year to ongoing soil degradation and soil loss. 0.3%. That's kind of a small number, right? I mean, that's kind of what we're all getting on our savings accounts, I think. Hard to notice the interest on a year-to-year basis. But if you think like a geologist, 0.3% over the next century, which to me is like tomorrow morning in terms of humanity's future, 0.3% adds up to another third almost of our global agricultural production capacity that we may be in the progress of degrading if we play out at a global scale the patterns that are playing out at present. And so it's my contention that these patterns, the ongoing degradation of soil fertility and our agricultural production capacity at a global scale is one of the really big challenges that humanity faces in the 21st century. We simply can't keep going at the rate and direction we've been going and expect to be able to carry it on for very much longer in the broad sweep of human history. In other words, I think agriculture is going to change in the 21st century. I think it is changing. And I'm optimistic about the change because of where I ended up by the time I finished Growing a Revolution. By the time I interviewed farmers and people like Guy Swanson and David Brandt and Gabe Brown, people who have been restoring fertility and life to their land, I've been given hope that we could reverse the pattern that I documented in dirt. Because 10 years ago when I finished that book, I actually struggled mightily in writing the last chapter because by the first draft I was really depressed. And I thought, I don't want to write a depressing book. This stuff is way too interesting to be that depressing. And so I ended up writing a third draft of the final thing, and it is what it is. But what I found in it was a very similar pattern in the effects of the way that ancient societies had treated their land and how that had affected their longevity. And it's no mystery. You can go back to almost any environmental history textbook and find the argument that soil degradation had undermined the foundation of many civilizations in the past. Whether it was Neolithic or Bronze Age Europe, classical Greece, Rome, the southern United States, as I sort of learned a lot about the background, about why parts of my own family migrated towards the west, that soil degradation played a role in that. And this is usually the explanation that you see in those environmental histories is that it was the axe. It was deforestation, it was timber harvesting that drove the soil erosion that impacted those societies. And having studied soil erosion on steep slopes in the aftermath of forest practices along the west coast of the US and in tropical regions for decades, I sort of realized that the numbers that you get from that don't really add up to explain the wholesale loss of soil off of whole regions like we've seen in some parts of the ancient world. For example, Syria and Libya. Not exactly the places we think of as agricultural powerhouses today, but if you go back to Roman times, we have tax records that document large harvests of wheat off landscapes that barely have any soil left and barely support their people today. This is the story that I laid out in dirt. And what I found was that it wasn't really the axe that generated the land degradation that impacted ancient societies. It was the plow that followed. It was keeping vegetation off the land. And when you think about that, how could that be? Well, think about what a plow does to the landscape. It inverts the soil, leaves the land bare and vulnerable to erosion by wind or rain for the time between plowing and when the next crop leafs out and comes in to protect the land surface. And how many of you have ever walked around a native grassland or a native forest anywhere in the world below timberline or outside of a real desert and seen broad swaths of bare land? Nature tends to clothe herself in plants, and for very good reason, because the production of organic matter and its return to the soil helps to build soil fertility, which helps more plants grow, and that's sort of a virtuous circle, if you will. And the plow undoes all that over time. In particular, it increased in the way that it affected ancient societies, is that it increased the vulnerability to erosion by wind or rain. And if you have a system where you are losing something faster than you're rebuilding it, and I'll show you some numbers in a minute about how fast that nature actually builds soils. If you're eroding soil faster than you're replacing it, you're literally running out of it. And this is no different than our bank accounts. We have income, we have expenses, we have savings. And I can vouch from personal experience that if you spend money faster than you make it for long enough, you go broke. Soil's no different as a system. If we erode it faster than we're rebuilding it, then we're running out of it. And how long that takes to play out depends an awful lot on how much soil there is on the landscape and what we're asking of it. And this picture of the Palouse region in eastern Washington, I'm going to pick on my own home state of Washington for a few minutes. This picture of the Palouse is from back in 1970, some decades after the establishment of the Soil Conservation Service. And it illustrates quite crisply, I think, why a geologist like myself would look at tillage as plow-based agriculture as something that really bleeds soil off the landscape. Because if you have any kind of a slope, and yeah, these are kind of steep hills, but it's an interesting region, and you have a winter wheat field like this one that had been fallowed, and then rain fell after it was plowed, all these little channels, these little rills that can develop, are things that you could just erase with a single pass of a plow, but that can add up over time. They could be an agronomic nuisance, but they can actually sap the vitality out from underneath a civilization if they go on for long enough. And how does that happen? Well, if you basically play that out, here's another example from the Palouse, that same region, photo by Vern Kaiser taken back in 1961, of what I like to think of as a fence line cliff, where the land was up at this surface in 1911 when the sod was first broken for planting. That fence up there is a fence that surrounds the water cistern that this farmer put in at the time that this field was first plowed. And the only thing that happened on this field between 1911 and 1961 when the photo was taken is that it was in a wheat fallow rotation for 50 years, and sometimes rain would fall or the wind would blow after the field was tilled. That resulted in over time of this cliff through here, developing at the edge of the field. And the two factors of erosion were both the actual tillage erosion, the average downslope bias movement of material when you plow on a slope, and those little rills that developed. Well, so how high is that cliff? That little black line right there, from there to there, is a 1 foot increment on a stadia rod, on a survey rod. This is a 5 foot cliff. These are not unique. You can find them around pioneer cemeteries in this part of the world. You can find them in the Palouse. You can find them in Central America. You can find them in places where tillage has been practiced over the long run on one side of the fence and not on the other. 5 feet of erosion in 50 years. That pencils out to about a foot a decade. That's about an inch a year. There is nowhere on Earth that soil forms at that pace, except my wife's garden and perhaps your farm. But we'll get there. Nature doesn't tend to form soils this fast. You should also be sitting there thinking that, Dave, isn't that a pretty extreme example? Of course it is. That's why I use it. I'm a professor. It makes my point. But it also should get you thinking and challenging how generalizable this is, right? Because that's the real question. Not sort of what happened on one particular farm over 50 years, but how is this played out over broader regions? How is this played out globally? What kind of perspective does this give us on some of those really broad brushed and crude things like that map that I showed you from the UN right at the start? So let's basically visit the American Southeast, a place that my ancestors left back in the 1830s and 40s as part of the migration that took people from the area of the hill country, the Piedmont, to points further west, in great part because of the better soils that were across the Appalachians. But let's look, do I want to look at this area, the sort of gray noodle up here? Because other people have gone, some of my colleagues have gone through and documented the historical soil erosion that happened in that region. So not in the broad coastal plain of the Carolinas and Georgia, not in the spine of the high Appalachians, but basically in that hill country in between. It's the area that you might expect to be vulnerable to soil erosion because it's not flat, it's reasonably steep. And you notice that some 4 to 10 inches of topsoil have been eroded off in about 200 years of post-colonial agriculture from across that broad region. In some places in those black regions, more than 10 inches of soil have been lost. Well, how big a deal is that? You go back and you read the original journals of the farmers and plantation owners from this area in the era when they were starting to farm, and there was only about 6 to 12 inches of fertile black earth across this region to begin with. So if we could quite literally plow off a third to all the topsoil across a region that was one of the major breadbaskets of the original American colonies, think what the Romans could have done with an 800-year run at central Italy. Think what they did to Libya and Syria. Think what the Greeks could have done to southern Greece. You can still find Bronze Age agricultural implements on bare rocky hillsides in southern Greece where there is no soil on the slope, where they were farming wheat in places where you could not farm today. It starts to put into perspective the idea that the long-term soil erosion could actually impact the course and fate of human societies, which was essentially the key nugget in that dirt book. And I got approached by a TV show called Nova that you may all know from PBS a few years back. I've done a few specials for them, or a few bits for them over the years. And I got a call when they were doing a show called Making North America, which is a 3-part series on the geological evolution of North America. They called me in the final stages of production and said, you know, we're almost done with this show and we realized that we've kind of left something out. Want to guess what that was? Soil! They had nothing on soil at the end, but when they were going into the end of production. And they called me up and said, hey, what could you do that would tell the history of soil across North America in 3 minutes or less? I said, wow, you know, that's the shortest summary of my book I've ever been tasked with trying to do. And I actually talked to Ray Archuleta about it and called him up and said, you know, Ray, what do I do to do this? And he actually suggested to me that, well, you know, maybe you go to a tobacco plantation, get a white tablecloth, and dig out a sample of soil from the modern tobacco plantation, and then go out and find a place where some land had gone back to forest for at least 100 years, and then compare them. And the TV guys thought this was great because, you know, it's drama. You have a shovel, you go dig a hole, you put it on a tablecloth, you compare them. And basically, this was the comparison. Which soil would you rather be farming? Which one do you think is from the forest? That one's from the forest, obviously. That one is from the modern tobacco field. And if you think that this looks a lot like beach sand, you'd be right. It's 10-million-year-old beach sand. It's Miocene beach sand. There's hardly any organic matter in it. You go to farms like this across that swath of the southeast, and there's no, in soil science terms, there's no A horizon left. There's no O horizon left. The topsoil, in other words, is literally gone. They're farming the subsoil. Think about where the fertility is in the soil. It's at the surface. You erode the topsoil off, and you've eroded the core fertility of the land. And this also is meant to remind me that there's another difference. There's two problems in terms of soil erosion and degradation. One is the loss of the topsoil, which is what I was looking at in terms of ancient societies. The other is the loss of soil organic matter, which you can see quite simply with the color difference between these two soils. There's organic matter over here, there's hardly any over there. If you look at what the average loss of organic matter from North American cropland soils is, the most recent estimate I've seen of that is roughly 50%. You look at the average loss of soil organic matter globally off of cropland soils, it's roughly 50%. In other words, we've lost roughly half of the organic matter from the land that we depend on to feed us. This should be viewed as a major problem. But when you look back at the ancient societies, and you look back at, say, Rome or Greece or something, and you're trying to calibrate what happened to their land, what happened to their soil. You can go there today and you can dig holes, but there's no one that was there 2,000 years ago collecting data and publishing it in a peer-reviewed journal that you can actually use to evaluate whether or not the rates of things that were happening back then are adequate to explain the conclusions that you might come to by looking at the archaeological record. So when I was writing the dirt book, I spent some time trying to figure out what are the rates that the world's cropland soils are eroding at present, how fast does nature build soils, and how fast do the soils tend to erode naturally? Simply to try and satisfy for myself, was the story I was coming up with in looking back at the archaeological record, did it make sense in terms of what the science that we know today? So I did something that's become very unpopular on university campuses. I went to the library. And I parked there for about 3 weeks. And I vacuumed up all the data I could find on how fast are the world's soils eroding in different settings. And I've boiled it down to a single table. I'm not intending to give a data-rich talk today. I published all the data that I came up with in an Excel spreadsheet in the Proceedings of the National Academy of Sciences. If there's anyone here who wants to follow up on this work, don't redo it. Just steal my spreadsheet and expand it and send it back to me with more data in it, please. But this is what I came up with. So there's different types of measurements, and there's different, and the averages or the median, so half the values that were lower, half the values that were higher, so that style of an average. And conventional, what I call conventional agriculture, tillage-based agriculture, plow-based agriculture, you look at, these numbers in parentheses, those are the number of peer-reviewed academic studies I averaged to get the numbers on the right. So conventional farms around the world are eroding at an average pace of about 1.5 millimeters a year. That's another little small number, unless you're a geologist. Your fingernails grow faster than 1.5 millimeters a year, or at least mine grow faster than 1.5 millimeters a year. The San Andreas Fault moves 10 times faster than 1.5 millimeters a year. And I've never seen it move in my lifetime. And I hope not to. But that number is actually really large when you compare it to the pace at which nature builds soils, which is, percents of 1 millimeter a year. It's really slow. It takes centuries for nature to build an inch of fertile soil. Long-term rates of erosion under native vegetation averaged around the world is kind of comparable to rates of soil building. That's reassuring because one of our primary observations in our personal experiences, wherever we go in the world, we tend to find soil covering the landscape. That's one of the characteristics, that's one of the things that makes this planet habitable. You have to go to special extreme environments to find places where the soil is either not very present or incredibly deep. And that makes sense, because with geological time at your disposal and thinking about this, if soil production was much faster than the long-term rates of erosion, we'd be buried in the stuff. And if soil erosion was much faster than soil production, there'd be no soil anywhere. So the fact that these three numbers at the bottom, long-term geological erosion rates, soil production, and short-term erosion under native vegetation, those are all roughly the same number. The difference between those blue numbers and that red number is frightening when you think over the long term. It's a order of magnitude or two that we're eroding soils globally faster than they're being produced. The good news is in this blue number right here, erosion rates for no-till agriculture. That's down in the range of rates of actual soil production. So this is sort of the good news, bad news slide. The bad news is, of course, that the way that we have long practiced agriculture is simply not sustainable over geological timescales. The good news is that the problem isn't that we farm, the problem is the way we've been farming. We can have an intensive agriculture through no-till agriculture that actually preserves and protects the physical integrity of the soil. And I'll get back to the organic matter issue in a few minutes, but if we look at what this means, I've given you the data now that we can sort of run the back of the envelope kind of calculation that I like to do with graduate students to predict what's the average longevity of an agricultural civilization. Because if you look at net soil loss on the order of 1 millimeter a year, and I could have argued for 1.5 millimeters, we'll go conservative, 2/3 of that the difference between that red number and those blue numbers was roughly 1 millimeter a year. That means you could erode off a 0.5 meter to 1 meter thick, a 1 to 3 foot thick hillside soil in roughly 500 to 1,000 years. That's about the average longevity of agricultural civilizations that I found when I was researching the Dirt Book. But there were some really important exceptions, the ones we tend to think about when we think about long-lived agricultural societies. And of course, that's the civilization along the Tigris and the Euphrates River in Mesopotamia that, the original descriptions of were as the Garden of Eden. Iraq and Syria don't seem that way today, do they? There's the Nile River in Egypt, farmed for thousands of years sustainably. There's the Indus and the Brahmaputra in India. There's the big rivers coming off the Tibetan Plateau to the lowlands of China. The big agricultural civilizations that have prospered for thousands of years are all in major river floodplains. And the key to their longevity lies in that last word, floodplain. Because what happens on a floodplain, unless you build really big levees, and we're not going to talk about New Orleans today, what happens on a floodplain? It floods. What happens during a flood? Sediment is delivered and settles out on the floodplain. And with the numbers that I showed you, with the average global erosion rate of about 1.5 millimeters a year, compare that to the thickness of a grain of sand. Sand tends to be 1 to 2 millimeters thick, sort of medium to coarse grained sand. All you have to do, in other words, on a big river floodplain is deposit a single grain of sand each year, and you can completely counteract the erosive effects of tillage erosion using this sort of crude global average number. In other words, we shouldn't be at all surprised that you could sustain farming using tillage on river floodplains for thousands of years. The numbers pencil out. Where you can't do it is outside of floodplains. And that's the experience that I've seen in terms of the experience of agricultural civilizations time after time. Now, of course, this should motivate the question of, are we doomed to repeat this historical pattern? And if I'd come up with that as the answer, I'd probably be living in my basement with a barrel of scotch and my guitar and quite happily waiting for the end of the world. But I think we can reverse it. I think we can completely reverse the historical pattern of soil degradation, and we can do it both profitably and rapidly. And where I started to actually learn this was in the most unlikely of places, my own yard. And why did I learn it there? Because my wife is a gardener. And she and I wrote The Hidden Half of Nature together, basically describing our experiences bringing our urban lot in North Seattle, where we live, back to life. So what was the deal there? Well, when I got tenure at the University of Washington, we finally realized, well, we can buy a house. And believe me, I am very glad I bought a house in Seattle 20 years ago instead of trying to do that today. This is the place we bought. The house is over there. It came with a side yard. Anne had always gardened the places that we were renting as graduate students, and the attraction of having this sort of lawn, a side yard that just had a lawn as something she could turn into a garden, major reason we bought the house. Then when we cleared that lawn off, we discovered that we had this incredibly rich, fertile black earth that Seattle is so well known for. Yeah, no, we had dirt. When we peeled that lawn off, we didn't find a single worm. There was not a single macroscopic life form living under that 6-inch tangled mat of roots that I like to think of as an old-growth Seattle lawn. It was really bad. We had glacial till, and this is stuff that was scraped off of British Columbia by a glacier that overran the Puget Sound region 15 to 17,000 years ago, bulldozed that stuff down, laid it out in meltwater streams in front of the glacier. Then the glacier, 3 times the size of the Space Needle, ran over it and compressed it into nature's concrete. This is what my gardener wife was confronted with when we pulled the lawn off, and we were like, oh dear, why didn't we dig a soil pit when we were looking at the house? We inspected the basement, we inspected the attic, we didn't think to inspect under the lawn. Fortunately, Anne didn't think of that either, so I'm not in trouble for it. But what we did do is we realized that we had only half of the recipe for fertile soil. We had the geological part, we didn't have the biological part. Because when you think of what makes for healthy, fertile soil, it's the marriage of geology and biology. And she actually is a biologist, so there's some parallel there. Keep that place in mind, the neighbor's house behind, it'll show up again in a minute. But what we realized is that we couldn't do anything about, well, we had all the mineral elements we needed in the yard. What we needed was the biology. So Ann painted up her wheelbarrow because that makes it go faster. And we started trying to get all the sources of organic matter we could to bring organic matter back into our yard. And that meant, raking up the neighbor's oak leaves in the fall. And, in a city, people are really happy when you show up with a wheelbarrow and say, can we rake your leaves? And you take them home to your yard. What they don't realize is that we should have been paying them for all the nutrients they were giving us. But people in the city don't think about that. Other sources, there's coffee shops all over Seattle. They put their coffee grounds out behind the coffee shop every night, and gardeners go and take them away. It saves the coffee shop disposal fees and gives us nice sources of nitrogen to put in our yard. Arborists were happy to chip up trees, get a great source of carbon-rich stuff, and if you got nitrogen-rich and carbon-rich stuff, you can start mixing them together to make mulches and compost. This is what Ann specialized in and what she loved doing, and started doing for years. The last source that I'll mention is that there's this wonderful material known as zoo-doo that you can get in Seattle, and as you might guess, it's produced by the herbivores at the Seattle Zoo, and they produce it by the truckload, and they need to get rid of it. We entered the zoo-doo lottery one year. We won, so we filled my pickup truck up with zoo-doo, brought it back, put it all over the yard, and loved it. It was great, so we entered again, and we won. And then we entered again the next spring, and we won. And we finally realized that you always win the zoo-doo lottery. So what did this do to our yard? After about 3 years, I started noticing, and Ann started noticing, that the color of our soil was changing. It was no longer that beach sand khaki. It was starting to get kind of chocolatey brown, and it's a little washed out on this slide, but you see her pruning shears there for scale. This is a pit that we dug. It was 3 or 4 years into bringing all this organic matter back to the yard, and you'll notice that we still have the glacial till at the bottom. We didn't rototill, we didn't dig, we just composted and mulched. Why did we do that? We were lazy. We didn't have the time to do it. We didn't think to do it. We just wanted to keep adding organic matter, and it would disappear. We'd add it in the fall, be gone by the spring, so we'd add more. 3 or 4 years of doing that, and we had about 2 inches of halfway decent soil at a place where we had nothing to begin with. This is and we were doing this when I was writing that dirt book, looking at the pace at which nature builds soils, centuries to make an inch or two, and if you take that number home, you go, well, we can't rebuild soils. Here we had direct evidence that we're building 2 inches of relatively good soil in a couple years. This pencils out that you could build like a meter of good soil in 100 years. What you needed was the organic matter and the labor and getting it all together. But this started me thinking that, wow, maybe we could actually turn this kind of long-term process around. And we started looking into what was actually happening that could turn the stuff that we started with that had less than 1% organic matter over here in my right hand into the stuff we have today that has about 10% organic matter. And we did this with compost and mulching in our yard, and we did it through gardening. We've stored tons of carbon in our yard, not because we were trying to offset climate change, but because we were trying to restore the fertility of our land. And then anyway, what did this do to our garden? Well, it resulted in an explosion of life above ground, both life in the soil and life, both animal and plant life above ground. The thing I'll point out, though, is that we can barely see the neighbors anymore. In fact, this is now grown up to the point where you can't see them. They're lovely people, but I got really tired of watching their kids grow up. We're on much better terms with them now that there's a green wall between us in the city. But this transformation of our yard from essentially what was a biological desert into a lush garden with very rich soil was something that it took Ann and I a while to figure out. Wasn't really our doing. We were setting the stage for the organisms that actually converted the soil for us. The trillions of microorganisms that actually live in the soil and in our yard. Because it was the transformation of the soil and soil life that led to the explosion of the plant life that was motivating us to build a garden in the first place. And as we started looking into that, we ran into studies on the rhizosphere, literally Greek for the zone around the roots of a plant, which turns out is one of the most life-rich areas on the planet. You want to find a whole lot of microorganisms, look around the roots of a plant. That's where they congregate. And Ann and I were trained in graduate school in looking at soils to look at roots as straws that drew nutrition out of the soil. And this is not wrong. They do that. It's obviously one of their functions, although it turns out it wasn't their original function if you look at the evolution of plants. The roots are to hold plants up. And we ran into the idea that plants are actually pushing out an awful lot of material from their roots into the soil. Things that are called exudates, because they're exuded out of the plant roots into the soil. And it turns out that plants can exude 30, 40, sometimes even more % of the material that they build through photosynthesis, combining CO2 from the atmosphere with water and mineral nutrients from the soil to build their bodies. They'll push out more than a third of that material back out into the soil. Why in the world would a plant do that? It makes absolutely no sense from a simple classical economics perspective. How many of us will take a third of our income and just go put it on a street corner somewhere? I certainly don't. Turns out that the reason is because they get something in return. All that microbial life living in the roots, in the rhizosphere, in the root zones of the plants, is primarily there because of this banquet table of exudates that plants are laying out for them, pushing essentially nutrients out into the soil, because what are in those exudates? Carbohydrates, proteins, fats. There's a paper that came out, I think, a year ago that looked at that plants pushing lipids, fats out into the soil. What are fats, proteins, and carbs? Food. They're pushing meals out into the soil. They're feeding those microbes. They're feeding the bacteria and fungi that actually live around the root system. And if that was something that they were primarily feeding pests and pathogens, do you think it would have evolutionary legs? No, that'd be shut down real fast if you think about geological time. Yet if we look back at the very earliest land plants that we have fossils of, there's mycorrhizal fungi wrapped around the roots. The mycorrhizae were the original sources of nutrients to plants. The roots actually just held the plants up. So what Ann and I realized that the rhizosphere, this zone of life-rich zone around the roots of a soil, is essentially a great grand biological bazaar. Because if you blow up the tip of a root in the rhizosphere and you look at what's happening there, the plants are pushing exudates out into the soil. Those exudates don't make it very far. They make it about 1 millimeter to 1 centimeter, the thickness of my thumbnail to the length of my thumbnail, away from the roots of the plants before they get eaten by something. And what happens to anything? It metabolizes it. So you convert stuff from one form into another. The input's not equal to the output. As we all know, it gets changed. And those microbial metabolites, or another word might be microbial manure, are being produced right in the zone around the root of the plant, in the area where they can readily be taken right back up by the plant. And so what are some of the kind of metabolites that bacteria in the soil are producing? We were astounded to learn that soil life are producing things like plant growth promoting hormones. And think about that for a minute. If you have bacteria in the soil that are producing hormones that cause plants to grow, you've got an organism in one kingdom of life producing a hormone to promote the growth of an organism in a completely different kingdom of life. It makes no sense unless there's this feedback. The plants are feeding the microbes are doing things that help promote the growth and health of the plants. And that one example is just the tip of the iceberg of all the chemical signaling and teeing up of plant defense and the provisioning of nutrition that's going on between exchanges between soil life and plants through this medium of the plants having a monopoly on photosynthesis, pushing food out into the soil, and recruiting particular communities of organisms that promote and benefit their own health. And if you have enough dense life of beneficial organisms, or even just organisms that are not harmful to the plant, that can crowd out pests and pathogens. Mycorrhizal fungi can actually hook up with the plant roots, send their hyphae way out into the soil where they can basically come out and take particular mineral elements out of soil particles, bring them back into the soil, and trade them to the plants. In other words, this is an example of symbioses, examples of these two organisms benefiting each other. And this can lead you to think of different models for how to think of plants having a diet. And I never thought about plants having a diet when I started working on this kind of thing and looking into it. But if you take a plant and you feed it the full complement of major elements that it needs, you can turn a plant into what Ann and I call a couch potato crop. And it doesn't invest as much in its root system, so it will be not putting as much out in the way of exudates. It will be getting in return fewer mineral micronutrients and fewer beneficial microbial metabolites. This is part of the explanation, we believe, for the historical decline in mineral micronutrient content, and in conjunction with crop breeding, obviously. But also, this is a good explanation for why pesticide sales went through the roof after fertilizer sales went through the roof. We disarmed plants' defense systems on a large scale and systematic way. Plants that are grown with the soil health diet, as we called it, in the hidden half of nature, grown with a lot of organic matter, invests a lot in the root system, they get more of these things. Different ways to think about feeding plants. This led me to think about, wow, could these ideas apply in agriculture at larger scales in our yard? It's one thing to talk about restoring soil in an urban lot in Seattle. It's a whole other thing to think about doing at scale on farms around the world. As a geologist, I was not the guy to tell anybody how to do this, so I took 6 months off of my job, went around traveling with people like Guy, visiting people like David Brandt, and going, okay, how do you restore soil? How have people done it? Take me to visit farmers who've already run this experiment, and I'd like to ask them how they did it. And I'll bring a shovel and dig a hole to look at their soil, because I'm trained to do that. But I went around and visited farmers around the world. What I found was that people who'd adopted the principles of conservation agriculture could match conventional yields using far less oil and chemical inputs. They were able to, and that was a recipe for better profitability. What are those principles of conservation agriculture? And I went to Costa Rica, I went to Ghana, I went across North America visiting farmers. These are the three principles that the farmers who had restored organic matter and fertility to their land rapidly, and by rapidly I mean within a decade or two, because to a geologist that's instantaneous. Minimal or no disturbance, which is where no-till and things like strip tillage come in. Maintained a permanent ground cover, the importance of cover crops and retaining crop residues, and diversifying rotations to have 3 or 4 or more crops, or cover crops that would bring that diversity in. These are the common elements. I visited people like Dwayne Beck, who I think has spoken here before, and he's from Dakota Lakes Research Farm. By adopting no-till cover crops and complex rotations over the period of decades and learning a system that would apply in their area of South Dakota, he was able to develop a system of farming that greatly reduced diesel and fertilizer and pesticide use while maintaining, if not increasing, yields. And if you decrease your input costs but you maintain your yields, that's a recipe for better profitability. I visited Kofi Boa at the No-Till Center near Kumasi, Ghana, who had applied these same principles in a completely different manner. The farmers he works with grow like 6 to 8 crops in the same field at one time. They do it by hand. This room would be a very large farm there. It's subsistence farming, and these are farmers for whom the idea of buying fertilizer and pesticides is kind of a non-starter for the very simple reason that they don't have any money. They're not going to be buying GMO seeds. They're doing everything by hand. He taught them a way of going from their traditional slash and burn agriculture, which once they were treating the same land every year, growing everything, not rotating that around the landscape, they were degrading their land. He turned off soil erosion, and what he'd do to their yields by going to no-till with cover crops, he tripled their corn yields, doubled their cowpea yields. This was transformational in terms of what they were doing. I visited David Brandt from around here. He basically walked me through what he was doing on his farm, and he was growing corn, wheat, and soybeans, plus getting diversity in with cover crops and his favored radishes. And he basically walked me through the difference between what he was doing and what his neighbors were doing. I'm sort of a bit short on time, but the bottom line is that his conventional neighbors who were doing full tillage and lots of nitrogen and Roundup were losing $100 an acre the year I visited or so. And with his 44-year-old no-till with cover crops, he was using hardly any of those, an eighth of the nitrogen, a fifth of the Roundup, and he was quite profitable at the same time. His yields were better, his expenses were lower. I visited Gabe Brown in North Dakota, who is bringing livestock back into his operation and regenerating the soil of the native prairie. He's basically terminating his cover crops using 4-legged mobile methane digesters. And what did it do to his soil? This is Gabe's soil from his market garden that's got the most attention on his land. This is his neighbor's organic farm. Which soil would you rather have? And Those colors should remind you a lot of our yard. So basically, I boiled this down, these sort of experience of these farmers I visited around the world, to 3 simple ideas: ditch the plow, cover up, and grow diversity. That's basically the recipe for conservation agriculture. And if you think about the philosophy that we had for most of the 20th century in terms of conventional agriculture, it was intensive tillage, add a lot of chemicals to make up for the things we're extracting, and grow 1 or 2 things. This is 180 degrees from where we've been teaching people for 100 years on how to farm. It's the basic philosophical difference. And I want to emphasize that that's not a question of organic versus conventional. Most of the farmers I visited were conventional farmers. I visited 1 organic farm. These ideas work in both systems to help improve both profitability of conventional systems and the sustainability of organic systems. And I'm going to breeze through these last slides because I think I'm out of time, but this basically, we've had, by my count, 4 agricultural revolutions to date. The idea of farming in the first place, cultivating and tillage, was revolutionary. The idea that planting legumes and rotating crops was discovered by societies around the world independently over time, and we were adopted because they work. Mechanization and industrialization in the 19th and 20th centuries, the 20th century green revolution of biotechnology. These are the agricultural revolutions we've gone through already. It's my contention that we're poised for basically following through on a 5th agricultural revolution that would prioritize thinking about soil health. And I think that this could improve farming in both the conventional and in the organic worlds, and that we ought to be looking at and evaluating farming practices through the lens of, do they build or degrade soil health? That would be truly revolutionary in the course and sweep of human history. And I'm excited by the farmers that I visited and their examples, because they show that it can be done, because they've already done it. It's not a theory. They've already demonstrated on their land. I view it as a challenge of experimentation to figure out how to apply these principles in different environments and how to teach people how to do it. There's lots of benefits that we can derive from that in terms of on-farm benefits, global benefits, and I'd encourage you to stop by my table downstairs afterwards if you want to check out one of the books. You don't have to remember any of this. I wrote it all down. And I should probably stop there. If we have time for questions, great. If not, come by and ask me at the table any questions that you want. Thank you.
All right, let's take one question or a comment.
David, I had a light bulb moment when you talked about 2,000 years ago and how they brought out the plow. And I got to thinking, man didn't live very long in that timeline.
Yeah.
And we judge our land by our lifespan. And if you made it, Jesus Christ made it for 33 years. I'm twice that now, or more. And, we keep looking at Billy Graham, and he made it 3 times. But we now know, and in our lifetimes, we can see it go down the hill. It's in the creek, it's in the lakes. Where in the hell were we thinking about? So now we have a chance. For the first time in human life on the planet, we have a chance to get the dirt in place and build it right there in one spot.
And keep it there. And you'll notice that of those 3 principles of conservation agriculture, 2 are ancient ideas. Cover crops and crop rotations are not new ideas. Combining that with the technology that allows us to do no-till, that is the revolution right there. Combining those ancient wisdom with our modern technology, because I think you're absolutely right. We're poised to be able to do things differently. And given our growing numbers, we simply have to.